Welcome back everyone. We are studying NPTEL course Topological Phases of Matter. We are now studying Berry phase. We talked about Berry phase in terms of wave functions, which is written as a curl of Berry connection in 2 dimensions, and the Berry connection was written in terms of states, and that becomes a curl of derivative of the states along 2 perpendicular directions. So, this is along mu n and this is along nu n, and we talked about that it is nothing but the fill for this covariant derivative to commute as we go into orthogonal directions. That is what we are measuring here. That is what it comes out to be, and the next step was to write this derivative, covariant derivative of the state of the fiber that convert that into the change of the Hamiltonian along those 2 perpendicular directions. All right, and there are few steps that you have to fill in as a homework, and what we obtain is that it is nothing but the derivative of the Hamiltonian along 2 perpendicular direction and divided by the energy difference. And to achieve that, if we were computing the Berry curvature along on a given band, nth band, you have to sum over all the other bands. Okay. So, every band's curvature knows the details of the other bands, and the underlying intuitions regarding that is that every state, as we move along certain direction, it changes in its basis, and the basis, the popular basis in condensed matter are the orbital basis. So, in this orbital basis it is changing, and that change is now placed into how the Hamiltonian is changing. And so, that means even if you are in a given state and how the state is changing, because the states are related to the orbital state with a unitary operator. So, it is expected that the other states, change of the other states do matter, okay, and that is how the other states summation enters into obtaining a Berry curvature, and the integrations of the Berry curvature was the Berry phase, and we will slowly talk about that as to be the Chern number. Okay. And the Berry curvature, the integration, which is the flux of the Berry curvature within this unit cell, gave us a quantity that we found in the previous chapter to be related to the quantum Hall effect, and with the appropriate normalization will show that quantity becomes a topological invariant, an integer value which does not change continuously, but it will change by an integer value. Okay. And we also relate this curvature and the flux of this curvature through the Brillouin zone as the TKNN invariant, which was related to the Landau labels. Okay. But here in this chapter we do not have any magnetic field. So, everything comes from the covariant derivative of the Hamiltonian. So, one more piece I require before I take examples, and that is Berry phase, Berry curvature, connection, and curvature in terms of the Bloch phase. Bloch states. So far we have talked about a general state, and eventually, because we are in a periodic lattice, how the total state for a given band or orbital, generally we write it as a product of it is also written as for a given wave vector, how the spatial variations of the wave function in real space look like, and we know that it can be split into a plane wave part and a periodic part. This is the periodic part. So it's which says K R plus R is equal to UN K R, and if you do the same thing about the K direction, it will be again periodic. Okay, you know those things from condensed matter 1, so I will not discuss much. It is just the some sort of a periodic part, plane wave like part, which is periodic, discrete periodic in a unit cell with different wavelength, and this is roughly the probability amplitude for each unit cell of and with that, so the Hamiltonian in momentum space is assumed to be this, and this is the Bloch state. Okay. So, with these two information and plugging this in the Berry curvature formalism, let us start with the connection, and this is a kind of a trivial derivative. So, I will do the essential parts, and this will be homework for you to fill in the remaining one. This is how the definition was, and you can see that it is a trivial homework. The plane wave part do not contribute, and it is also the derivative in the momentum space. So, one may wonder what is happening with the real coordinate here, which is supposed to be here, and it is a local one, and the R part is already integrated in this definition of inner product. Okay. So, it is the derivative of delta k, and just to in the passing, let me make a comment that if I combine this term with this I and this, so which is like this. So, recall that in the position space a momentum operator is written as a I times derivative in the position variable that gives us the momentum, which generates a translation in the momentums in the real space, and here it is the opposite. In the momentum space, a derivative in momentum with I gives you a position, right, and this has to be periodic. So, those things we will talk about later, but roughly this is sort of telling you how the states are localized in real space, and we will see that these localizations will lead to a localizations of the state at the edge, whereas because of the periodicity there will not be any localizations in the inside the system, but this sort of things will lead to a localizations in the real space. And also we will be able to connect this to charge pumping that we talked about, that if I have a topology, it leads to a pumping of the charge from the bulk to the edge, from one side of the edge to another side, and this is roughly what it does. It will lead to a polarizations. So, that means this is kind of a polarizations, right. This is some side remark. So, what we have is yes. And the curvature then would be for a given nth band mu, and this is nu minus mu nu, right. This was the definition, and if you substitute this here, you will see a double derivative, and that can be written as the derivative in the brass state and the derivative in the gate state for the same band. Minus the failure for this two derivative to commute. So, again this should be trivial for things for you to derive, and in terms of Hamiltonian, terms of the Kubo formula that we obtain here in terms of the Hamiltonian will turn out to be same. Okay. Let me write it for completeness. So, H is in the momentum space. So, minus what we wrote there, mu and nu has to be interchanged. Right, and generally that is just band velocity operator. Okay, with the h bar factor, 1 by h bar. If you write it in terms of h, then it will be times h bar. Okay. And then of course, we can just finally write the Kubo formula in which we obtain the Hall conductivity for an electric field along new directions, and we are computing the or the other way, actually does not matter, there will be a sign only, that the electric field is along mu direction and we are measuring the Hall voltage along new direction. And generally we take it to be x y in a 2 dimension, and we sum over all bands. One can also compute it as a computations, we can compute it for each band, but what we measure generally is for all the field bands. So, we have a integration over all k, but only the states below the Fermi level. Okay. And this is the quantity we call Chern number, which will then give us I am supposed to have a summation over all n, all the states which are filled. At finite temperature, one can just add a Fermi data distribution for each k here, that will do the job, and otherwise that is included in this summation, restricting the summations below the Fermi level at 0 temperature. So, this was led to all the states which are filled. And this one we call Chern number. For the magnetic field case, this was what we called as Tikkanen number, and mathematically they are the same thing. So, okay. So, let me first write the summation. And if the momentum in the thermodynamic limit, if the momentums are small, the grids are small size, we generally write it as an integration. K B Z, and now one can just add a Fermi Dirac distribution function for, so that we do not have to carry this thing, you can just integrate over entire Brillouin zone. Okay. So, it is the flux of this Berry curvature through the Brillouin zone is for a given band is what we are measuring, and we claim it to be integer, and that is what we want to show. Before that, we need to build one more intuitions about in what sort of system this finite value of this Chern number will appear, and in what sort of system this value will be 0. Okay. And this is an important chapter. Origin of non-trivial topology. The origin, we will connect it to two things. Okay. So far we have only mathematically developed the Berry curvature as the connection in the wave function, and that connection we saw in the first chapter is to arise from how the states or the frame, in this case roughly the how the orbital states in which the eigenstates are written are rotating as we take a derivative of the state, as we go from one point in the momentum space to a nearby point. So, one can wonder now, the Brillouin zone is the Brillouin zone, right, and the Brillouin zone, how come a Brillouin zone becomes trivial in one case and non-trivial in another case? So, it is not the informations in the Brillouin zone, it is the information in the eigenstate and the Hamiltonian which we just derived. So, now there will be some Hamiltonian in which there will be a non-trivial topology, and there will be some Hamiltonian in which there is no topology. And we learned that topology being the has to do with the topological space in which we have fibers every point, right, and here the topological space being the Brillouin zone, right, and how the fiber is changing in the Brillouin zone, or how the eigenstates are changing in the Brillouin zone. So, how come a topological space, the base manifold changes as we change the Hamiltonian, right. So, it is actually the homeomorphism from the Brillouin zone to the parameter space of the Hamiltonian, and within that parameter space of the Hamiltonian, you will see that there will be some case in which, and also you remember that a non-trivial topological space means a topological space in which cannot be covered with one chart or one sort of a coordinate system, if you like. If that happens, then it is kind of a RD, right, it is just a real space, just the numbers in which everywhere we will just have one sort of a coordinate system, and there is no curvature in your topological space. On the other hand, a non-trivial topology is, for example, a Mobius strip and so on, in which you at least need more than one chart, and in different chart then you will have different connections, and we have seen that in the case of Aronovo-Bohm phase, that if I have this geometry in which a magnetic field is passing through a solenoid which sort of made a hole in your topological space, so the wave function which is going through it sees it as combination of two connections, one connection that covers the north pole and one connection that covers the south pole, and the difference between those two connections is a gauge invariant quantity, and that gives us the topology. So, in this case there is no magnetic field, but there is still a topology that will arise which will be related to showing that the Hamiltonian space will have at least two or more connections which will be related to something called band inversion. And that will be related to having more than one connection or gauge obstruction. Connection or gauge fields are always arbitrary with respect to a derivative of a scalar function, but we will see that that condition will violate in a non-trivial topology in which you still have the gauge freedom, but there has to be at least two charts in the Hamiltonian space in which each connections will be arbitrary with respect to a constant with respect to a trivial gauge transformation, but the connections between two space will differ by a quantity that remains invariant under any gauge transformation. Okay. So, roughly speaking, what I said so far is that I have some Brillouin zone, and let us take it as a 2 dimension, and I have all these points, and I want to go to a Hamiltonian space in which I should be able to write a Hamiltonian in terms of parameters which we define. I will define again in the next one better way, or I will let me take 2, and let us just take as an example as being a 2 by 2 Hamiltonian, which we learn that, and we will see again, can be written in terms of Pauli matrices. So, and this D are kind of your tight binding hopping with the Bloch phase. So, for example, minus 2 t cos k x plus cos k y as an example. So, that takes you from every point to the Hamiltonian space, and then it will create some curves and loops. Whether this sort of loops see some hole, and you will see that d equal to 0 is actually a point in which things cannot be defined properly. So, that is like a hole in which some sort of a flux is passing through, or some monopole, Dirac monopole is there. Okay, we will see that. So, then whether it makes a loop as we sort of go around the Brillouin zone, which covers this Dirac point or not. If it covers, then you do have a Aronoff bomb like phase due to this Dirac monopole. Okay. So, that is what we are going to look into. Okay. So, what we do is that let's introduce the idea of band inversion. And that is related to so one may wonder, we are sticking to only one band in which we can compute the Berry connection, Berry curvature, Berry phase, and also we have an adiabatic theorem that is intact, that we said earlier. So, that means we are supposed to stick to just one band and compute all these things. So, then what do you mean by really a band inversion? And this is a very confusing statement, but I want to clarify it. Before we proceed. So, let us start with some example. Okay. In fact, before doing that, let me just start the gauge obstruction. So, under a gauge transformation, we know that the states are arbitrary with respect to a multiplication of a phase, and if that is the case, the Berry connection changes to within the same band. How the vector potential changes? And if that is the case, so that means Berry connection indeed is arbitrary with respect to a derivative of a scalar function. And this is still the entire theory remains gauge invariant, as we have also studied in the case of magnetic field, as long as the connection is changed by this and the wave function obtain that same phase. So, in that case, the Berry phase, that is the important part. Also changes to okay. Now, you see that the Berry phase also changes to the change of this phase. So, that means it looks like the Berry phase is not a gauge invariant quantity, and anything that is not gauge invariant is not a physical quantity that we cannot observe. So, what is going on? And what we will see is that indeed that is the case, Berry phase is, and let us say we are in some periodic boundary conditions, that means we are sort of going around the periodic lattice from some k point to k plus g, that is how we obtain a loop, and your wave function is supposed to come back to itself with a phase of 2 pi. So, the Berry phase we get is always arbitrary with respect to a addition of a 2 pi phase or 2 pi, 4 pi and so on. Okay. So, what is this obstruction then? And now we are going to show is that it is not the phase that completely obtained by a connection itself, because I can always choose a function. I mean, whatever the Berry phase I get, I can always choose a function, and this is the theory is arbitrary. You can always choose a function to make that quantity vanish. I can choose whatever the value I get for a given connection, I can always choose this to make this vanish. So, it should be a trivial case, but only for a non-trivial case we will see that there will be a difference of this between two regions of the Brillouin zone, such that the difference between that cannot be made to vanish. You can always add this quantity to each connection, but not to the difference, and that is what will be related to band inversion. So, to do that, let us assume some 2-level system, okay, and some h psi 1 equal to E 1 psi 1, psi 2 equal to E 2 psi 2. So, I will choose psi 1 or U 1 as the Bloch part of the phase, or psi 1, and both, as we just saw that both will lead to the same expressions for Berry curvature and all. So, even if I write psi 1, you know that it can also be obtained in terms of U 1, which are the Bloch states. And now, let me and some k space energy. So, let us say I have some E 2 psi 2 and I have some E 1 psi 1, okay, some 2-level system, and this is completely arbitrary. So, there can be a gap between them, there may not be a gap between them. So, this is completely arbitrarily drawn. And now let us do something interesting. So, let us write psi 1 in terms of psi 2, they both are eigenstates and they are orthogonal to each other, but I can always write it this way: psi 1 is equal to psi 2 multiplied with some constant, which is again a k dependent. I mean, not constant, I mean I am just defining R as the as psi 1 by psi 2 by just dividing psi 1 with psi 2, and I can always define it, and R in general is real complex. But what I will do is that I will just use it as a phase with setting the amplitude of this complex number to be 1. Why I can do that? Actually, we cannot do that, but the point I am going to use here is that the amplitude will not contribute to anything I am going to define below. That means, it is not going to contribute to the Berry phase. It can give you some number which can always be, because we will take the derivative, you will see that derivative can always be taken to be 0 with some suitable choice of the gauge. Or if I take a amplitude which I can take it as a log in the exponential, and you will see that the log of such an exponential once you take the derivative, when you obtain the Berry connection and curvature can be said to be 0. Okay. So, this does not violate anything, just take a phase, does not violate generality, just simplification. So, once we do that, as we just derived earlier, the Berry connection for band 1 now can be written as the Berry connection of band 2 plus the change of this phase. As we just obtained here. Okay. So, now let us take a trivial case, or let me do it in the okay, and then the phase will be phase of band 1 is equal to the Berry phase in band 2 plus the phase difference between the two eigenstates, if you like, right. This is what this quantity is. This is the phase difference between the two eigenstate. So, in the trivial case, I have, and let us do it 1D. And some Brillouin zone being somewhere here. Okay. As we go from here to there, minus pi to pi by a, I am always in the electron that is in band 1 is always in band 1, and the hole that was in band 2 is always in band 2. Okay. And now you can see that there is no change between or exchange between the state or anything, but they are orthogonal, completely orthogonal to each other, and you can make you can always choose some chi to make them to be 0. Okay. Let us take the counter example, that will be easier. So, and everywhere I will have A1 or A2 connection for each band, and you can always, because they are arbitrary, you can always choose some gauge to make them to be 0. So, the counter example is Okay. So, what am I drawing? So, what am I drawing is that let us say this one was E1 psi 1, and here after certain point k star so I am sticking to some band E1 which was psi 1 in this region, as in this case also E1 psi 1. But we see that it changes to adiabatically, there is no singularity or anything, just continuously change to the band index E2 for psi 1, and that looks like it violates your adiabaticity. But the idea is that if I stick to a given band and saying the eigenvector has changed, that follows our adiabatic theory. So, our eigen energy remains same, continuous, is just the state changes, that is allowed within the adiabatic theory. It is just a matter of how do you sort of define it, or kind of a name. I can stick to a given energy eigenvalue and then its eigenstates can change, which is allowed, or I can stick to an eigenstate and its eigenvalue can change, right. So, here the way I have defined is that I am saying that the eigenstate remains the same, but the eigenvalue is changing. And if somebody comes and define it this way, that E1 psi 1 and this is E1 psi 2, and it will be the opposite in this case, that is also perfectly fine, that is completely consistent with your adiabatic theory, that I am sticking to the same energy eigenvalue and the state has changed. So, it is just a matter of what you call, which one you take it as an index, and generally this could be your states eigenvalues are the index. So, that is kind of a better way to say it, and that is what we mean by band inversion. Within the same quantum number, the band has changed. Okay. And if this happens, so underlying what has happened is that each band was written in the orbital basis. In the orbital basis, the two orbital has changed, and those things you have seen it in the tight banding model or even in density functional theory induced band structure. When we plot the orbital weight on each band, we see that even in a given band the orbital weight changes continuously, and that will indeed show up here. Okay. So, in this case now, so if I go back to this nomenclature, in this case, in this region up to here, the connection is 1, and in this region the connection becomes a 2, if you define it in terms of the energy eigenvalues or Hamiltonian. Okay. And also here it is a 2. So, in 2D, so this is shown in 1D. If you do it in 2D, kx and ky, I will have some region which is a contour of k star, such that it will be A1 inside and outside it will be A2. for whichever directions we choose. Okay. If this happens, and we will show that if this happens odd number of times, then what we can do is that we can take a contour here, this entire contour, the integrations over entire contour, I can split into this for all these points here and this, all these points, the contour will look like opposite, right. For all these points the contour is now the opposite. So, which immediately tells us that becomes, so it is 1 within the region contour of K star and minus contour of K star, the reverse contour, and that we already include as a minus sign here. And now we see that it only depends on the phase difference between the two states, and you can do it over any of this contour where the phase change is happening. And this quantity is gauge invariant, because it is just the obstruction that the two eigenstates are different by a phase that you cannot get rid of, because you can always add a gradient of some scalar function, but that gradient will drop out from this minus sign between them, but what will always remain fixed is the phase difference between them. Okay. And this is the gauge obstruction between two states, which is related to band inversion. In the next class, I will take example to demonstrate how a band inversion arises in a Hamiltonian, and such that this sort of phase difference will always appear. All right. Thank you very much.